Hello. Today we're going to talk about Topic 4, Section 13, Non Linear Regression. So, models are super important for a whole bunch of things, okay? But how can we determine how well the model fits the data being tested? Okay, how do we quantify the effectiveness? Well, that's when our correlation comes into play, right? And those are powerful tools in identifying patterns, okay, and how well a model matches the real world. So let's do an example. And here we have pop time versus height. Okay, so we've got 5 different catchers. Usually you'd of course have a lot more data than that, but for our purposes, we're just going to keep it at 5. So we want to find the mean point. So we want to find the average pop time and the average height. And that's simply adding them all up, dividing by how many there are. There you go. We can also get the linear regression line with our calculator. Okay, we've done that before. Hopefully you remember. All right, so why is the regression line shown considered to be the line of best fit? What makes it the best? Okay, notice that our mean, our average point, all right, our average pop time and average height are on our regression line, all right, and we can estimate whether or not it's best or not based on the residuals, okay, the distance from the observed points and the expected, which would be the line. So first we got to get the estimated times, the approximate, right, using the line there. So we plug in our height. So put 69 in here. So let me show you. So we get y equals 0.04856 times 69 minus 1.52158. And that is going to be this number, which is 1.829. And then we do it again for each one of these numbers. Right, we've seen this before, right? We get our estimated by plugging them into our line of best fit. And then here, I just didn't want to give it away. Okay, so you find the sum of all the residuals of the data shown in the table, add up all the residuals. So the actual time and estimated time, so you would do actual minus estimated, observed minus estimated. All right. Oh, example 3, I kind of covered up the question there. Oops. Find the sum of the square of the residuals. So now we square all those differences. Okay. Now here's what you want to notice. SSRES, that's the sum of the square of the residuals. All right, so hopefully this is all looking familiar to you. All right, this hopefully is feeling kind of basic, right? Because now we're going to look at it from a different angle. Okay, so now we're going to find the total sum of the squares of the distances between each data point and the mean pop time. So we're looking at the average pop time, and now we're looking at the differences between those values. Okay. Oh, like it's all the way down there. Interesting. All right. So now notice how I write it. The notation SSTOT. Okay. So the total, it's this total sum of the squares. All right. So it's going in the other direction. So notice we took 1.81 minus 2.04. We're still using that pop time. Okay, the observed. But now we're subtracting the average time and getting this. Okay, so you're probably like, why do I need to know all this? Well, to get the coefficient of determination. All right, so this is your R value. It's just a fraction. So all we need to do is take the opposite of the percentage. All right, so going back to our example. All right, and the pop times with Ben's regression line. Okay, so the sum of the squares of the residuals divided by the total sum of the squares, all right, is 0.42. Do 1 minus that, and that's your R value. That's what I mean by opposite. Okay, so the regression line accounts for 57.9 of the variation. All right, variation of pop times of the given heights. Okay. Okay, so now let's talk about nonlinear regression. You need to make sure you know how to do this with your calculator. So not only linear, but quadratic, cubic, exponential, power, and sine regressions. So Yoojun is doing a study on the temperature trends in Seoul, South Korea. So this is the data, so all the dates, okay, and the temperatures. So you put all this into your calculator. Okay, I put the days as list 1, my temperature as list 2. I typically like my x values to be list 1. It just makes it easier for me to remember. When you plot them, this is your scatter plot. All right, so now we need to create different regressions. So for a linear model, all right, in case you forgot, you can go through these calculator tests and notice that that line is not a good fit. Okay, it's not even that great of an R squared. Okay, so that is not helpful. All right, so then we notice, okay, it kind of looks more like a quadratic. So we do that. All right, now one thing I do want to point out is notice that in on Cognity, they got 0.797570, and I got 0.795915, right? Our values are a little bit off, and that sometimes happens based on the calculators that we have. All right, some of the newer ones may be more exact, the older ones round a little bit earlier. It's just how technology works. Okay, you will not be counted off for those little variations as long as you are showing the correct methods. Okay, and notice they were both 0.79. Right, roughly, right, or I guess 0.7 or 0.80. Okay, if we rounded, that's okay. All right, so a quadratic model seems to be a very good fit. However, you could start to think, well, yeah, that makes sense for the data in just 1 year, but if I keep going, the temperature isn't going to keep decreasing, right? We're not going to become solid frozen and forever. Okay, the temperature will eventually come back up. So decided to create a sine regression, and this one actually makes sense. Now for the iterations, you can pick a number between 3 and 16. It just kind of I think goes to how exact it is. I think that's how they described it. So if you say 16, your calculator will tend to go slower. So you'd be fine leaving it at 3 as a default. Okay, I stored all of these lines, okay, are all the equations, so that way I could graph it with my scatter plot, and then I just screenshotted it. Okay, so here I tend to like the sine regression the most, because if you think about it with your data, it makes more sense. Okay, and there's a slight variation in, notice the iteration, so it really doesn't matter too much. Okay. All right, so this is what you need to know. All right, so really I wanted to show you this fraction just to understand the meaning of the coefficient of determination. Okay, you won't be expected to use it, but you want to know where it comes from. Okay, because there might talk about the sum of the squares, right? All that good stuff. All right, if you have any questions, see me in class.